All right, we looked at displacements and angular displacements in radians, revolutions, and degrees. Now we're going to actually do the angular velocity portion, the W. Why the W? We're out of V's and everything else. So when you do angular terms, we tend to go Greek because you know how much the Greeks love to go in circles. Look at their architecture. Is the rate of change in angular displacement. Okay, it's how quickly the angle is changing. Common in physics is radians per second. In America, yeah, we love our revolutions per minute, as they do in a lot of places in the world. But radians per second is kind of the standard. It just makes converting into other units much easier if you keep in those units. So instead of a distance per time, as speed would be, it's a angle per time. And technically there is a direction of this stuff. Now it's not going to talk about it in here, but we'll get to it at the end of the year. It's called a right hand rule. And the rule is you put your hand curls, your right hand, in the direction that something spins, and where your thumb points, that's the direction of the angular velocity. Yeah, it's perpendicular to the spin, and it's weird, but we'll leave that for coming up of why that might make a little more sense towards the end of the year. We don't have to know a direction right now. We're really just doing angular speeds, actually. Okay? Alrighty. So the angular velocity can also do what's called an angular frequency. I don't call it angular frequency. It's still angular velocity. It's just another fancy name. The reason is frequency means the events per time. Technically, a radian is not a full event. It's just a radian. But a revolution is a full event. So because it's a full event, you go revolutions per second, that technically would be the angular velocity. Now in this country, we do revolutions per minute normally, not revolutions per second. Okay? But F is used for angular frequency sometimes, but it's really the same unit. It's not any different, guys. Okay? It's still an angular speed. You're just doing this in revolutions per second rather than radians per second. I know it looks complicated. Think if you're in radians. How do you change radians to revolutions? Times 2 pi. Because its frequency would be just the your revolutions per second. Oh, I'm sorry. So if you want to convert this back to radians per second. So long story short, you don't need this. This is what you need. If you want to do revolutions per minute, perfect. It's still an angular velocity. Okay? So some people in the physics world, they call it an angular frequency. Whatever, it's still an angular velocity. Alrighty. So here we have another rope wrapped around a drum. I know how much you guys love that. This radius is shorter. It's 1/5 of a meter now. 1/5 of a meter. What is the angular velocity of the drum if it lifts it in 5 seconds? So we got a lot of choices, guys. I love choices. My thing is I'm going to take 10 divided by 5, and that's 2 meters per second. That means the outside is moving at 2 meters per second. So now if I know the 2 meters per second, all I have to know is what the radius is. Well, it's 1/5 of a meter, 0.2 meters. So if I divide out by the 0.2 meters per 1 radian, bam, I'm done. This is going to work it backwards to that. This is going to actually convert this, I believe, probably into radians, and then we'll go from there. It all works. Yep, that's what they're doing. So it moves 10. The arc distance it moves is the 10 meters for the 1/5, so times 5, that's 50. 50 radians it move through. Okay? So now it's just 50 radians per 5 seconds. It's 10. You're done. So it doesn't matter which way you do it. One's not really harder than the other. Okay, there's a lot of ways to do the same thing. So the angular speed of this thing is 10 radians per second. So in 1/1000, it's gone through 10 radians, or more than one turn. Okay, more than one turn. Because remember, in one turn, it's 6.28 or 2 pi radians. All right, keep on rolling, guys. We'll finish this sucker out here in a moment. So in the previous example, what is the free? Okay, so it's 10 radians per second. What's the frequency of revolution? I think we're probably going to go into revolutions per minute, so we have 2 conversions. It's not a fancy equation. They might try to give you an equation. It's just a conversion. It's still revolutions per minute or revolutions per second. It's still angular velocity. It's a different unit. Okay, so once again, they're trying to do something fancy here. That's not exactly what I would do. What I would do is take this you're going to divide by 2 pi, and it's really what the same thing they're doing. Divide this by 2 pi radians times a revolution, which is exactly what they did with this. It just looks funkier and makes it harder than it really is. Okay, in fact, so let me just go ahead and show you. I got a little bit of time here. What are you guys doing with your time anyway today, huh? I know. So all I would do is just take this times 1 revolution, that's a revolution, divide by 2 pi radians. The radians cancels out. Now I'm in 10 per the 2 pi, which is the exact same thing they did right there. It looks fancy because they're using equations, but it's really the same thing. It's just a conversion. I don't want you to make it harder than it really is there, okay? Click. Oh, now we got to do the per minute thing. Okay, so if you're in revolutions per second, you got to get rid of the seconds. So seconds goes on top, 60 seconds goes on top, the minute goes on the bottom, and shazam, there you go. It's just, that's per second. Now you're going to do it 60 times because it's per minute. So it's just a conversion times 60 divided by the minute. It's 95.5 revolutions per minute. Now, they didn't ask for that, so you didn't have to go to revolutions per minute. There's nowhere in the problem does it say revolutions per minute, but in America, that's kind of something that we do quite often. Okay, so it's making 95.5 turns every minute, so it's more than 1 turn per minute. All righty, 95.5 RPM, there it is. All right, angular and linear speed. So here's how we're going to convert between the two rather easily. Okay, so there's your linear stuff, there's just the radius length, and there's the angle you're moving through. Okay, so really all you're doing to find a speed of something is your distance traveled, distance, that's what the S is, the distance on the outside per the time. And then that's a distance per time. If you want to convert that into an angular speed, well, then you're going to have to divide by the radius. So long story short, this would be in radians per second, and that's the length of the radius. So never put a RPM in, don't put a revolutions per minute in there, don't put a revolutions per second. Because you're multiplying by the radius, you have to be in radians per second. And then you pop this right at whatever unit you are in the R is the unit of distance per the time for the velocity, which is a tangential velocity or just the speed of the thing. Okay? So long story short, to find the linear speed, how fast it'd be going in a straight line, if it was going in a straight line, or tangential velocity, angular speed times the radius. Done. That's all you got to do. Or if you're finding this, the actual speed at that radius divided by the radius, and bam, you're back in radians. All right, let's do a quick example here, or a couple of them. So we got 2 things. All right, which of those is moving faster, guys? Huh? The outside or the inside one? They're stuck on the turntable that's spinning, by the way. Okay? Well, the whole disk makes 20, has a final angular speed of 20 radians per second. Okay? So it takes 4 seconds to do that. So it's an angular acceleration. That's a topic for the end of towards the end of the year. We're not going to address the angular acceleration. We're only going to do the angular speed on this case, versus the tangential speed called the linear speed. So what's the final speed at points A and B? Well, they both have a final angular velocity of 20 radians per second, because it's the same radians per second anywhere on here. You have the same number of turns per second. But what's different is the speed. Guys, this is twice the radius, and it takes the same time to go around. How much faster is the bee going? 2 times faster, because it's twice the distance in the same amount of time, right? So we know it's going to be twice as fast as to see how fast. Now all you have to do is plug stuff in, but you got to be in radians per second, because 0.2 meters is the radius. So they're not showing it on here, but technically this right there is, oh, son of a gun. Gotta learn how to use this thing. So this technically is per radian, even though they didn't put it there. So the radian gets canceled out. It's meters per second is the unit, hence there you go. Okay. Then in the outside one, it's just twice the distance, and it's going to be twice as fast, the 8 meters per second. So it goes 4 meters every single second, it goes 8 meters every single second. Any questions? Good. Alrighty. Okay, guys. I don't know what it is with ducks and computers, but they don't get along. They don't get along. All right. Have a wonderful day, guys. Have fun at the homework.